Okay, so let's talk about the complex logarithm. So first, let's recall for the reals. The real logarithm going from 0 to infinity to 0 to infinity is defined, minus infinity, is defined as the inverse of the exponential. So log of x is y if and only if x is e to the y. Okay, so that's the definition for the reals. For complex, the same definition has worked. So the complex logarithm so log mapping from the complex to the complex is defined as the inverse as well. So of the complex exponential. So so log of w is equal to z is equal to w if and only if z is equal e to the w. Okay, so that's the definition. Let's do an example to get a handle over this. Find log of z for z defined as 1 over square root 2 and I over square root 2. The trick will always be to write this in polar form. So that we get the exponential. Okay, that's always the method. Okay, so we ask for some theta so that z is equal to the modulus of z times its angle. Okay, so first, what is z? So recall, this is the square root of the square of the real part plus the square of the imaginary part. Okay, so we get 1/2 plus 1/2, 1, and square root of 1 is 1. So the modulus is just 1. And right. And theta is the argument of z. And so, right, so we have arctan of the imaginary part over the real part. So we get arctan of 1, which is pi over 4. Okay, so that's the angle and that's the modulus. So we have log of z is equal to log of 1 times e to the I pi over 4. Okay, now we use the definition. This is the We're trying to find the W, right? And this is Z. But what did we say? We said Z is equal e to the W, right? And now we know what Z is. Z is e to the I pi over 4. So we get I pi over 4 is W. Okay? So log of Z is I pi over 4. Okay? So far so good. Now let me make a comment here. Observe. So you've seen from previous clips that e to the 2 pi I is equal to 1. This is Feynman's most beautiful formula. I mean, without, we don't have a minus here, but it's close. Okay, but the same is true if you do it to any power. Okay, for any n 0 plus minus 1 plus minus 2, so on. Okay, so what's the point of that? The point is that we have Z is equal to e to the I pi over 4. But then this is the same if you multiply by 1, where, so using our result, we have this is ei pi over 4 times e2 pi n. Okay. Now take log of both sides. What do you get? Well, you get log of Z equal to log of ei pi 4 plus 2 pi n. So as we did above, this becomes I pi over 4 plus I 2 pi n. But n can be any integer. So we have the following issue. Z got mapped to the following values. Pi over 4 plus I 2 pi 0, pi over 4 plus I 2 pi 1, 2, and so on. And then we can even go above. Minus 1, and so on. Let me draw a line. Okay. So this is the first instance of a multi-valued function. Okay. Let me draw some pictures to drive the point. So what's happening here? We started with e to the I pi over 4, and log maps it to the following. So let me go a bit above. So we have the 0 guy over here. This guy is over here. We have the plus 2 pi. This guy is over here. Let me draw one more. And then one below. Okay. Plus I to pi minus 1. And so on. So a single point got mapped to multiple points. One way to see this pictorially is that if you move in a full circle, so you get back the same point. But here, you're moving up one level every time you rotate. So every time you rotate counterclockwise, you go up. And every time you go, you rotate clockwise, you go down. Okay. So that's the intro to log.